Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, we are moving on to Lab 4, where we will learn how to build a complete SoC architecture using Vivado's IP integrator. In our first 3 labs, we focused primarily on hardware logic design within the programmable logic. Starting from this lesson, we are going to introduce the processing system and utilize the Vitis platform, learning how to build a complete system where hardware and software seamlessly work together. Here is the outline for today's session. Before we begin, please ensure that you are fully prepared. For detailed content, please refer to the pre-lab course. The core objective of this lab is to master the concept of system address mapping. Within an SoC architecture, the CPU controls the LEDs or reads the status of the slide switches by simply issuing read and write commands to specific memory addresses. By utilizing C programming instructions, we can write data into a designated address to light up the LEDs, and read data from the switch address to display its real-time status on the terminal. Inside the block design workspace, we have configured the Zinc 7PS to act as our processing core, alongside 2 instances of AXI GPIO. Connecting them is the AXI interconnect, which handles the arbitration and protocol translation of the bus signals. All control commands will flow through the AXI protocol, traveling from the CPU side down to the peripheral IPs on the PL side. Additionally, the processor system reset module ensures perfect synchronization of the clock and reset signals across the entire system. Please take a look at the address mapping table at the top of the slide. These are the addresses automatically allocated within Vivado. As you can see, the system has assigned a base address of 0x4120_0000 for the LEDs, and 0x4121_0000 for the slide switches. These two 32-bit address spaces act exactly like the house numbers for software to access hardware. Notice that currently, we are only utilizing 8 bits of this space to correspond to our 8 LEDs and switches. During the hardware design phase, it is crucial that we verify these addresses in Vivado's address editor window, because the software-side drivers will rely entirely on these definitions to interface with the hardware. Our workflow is divided into 2 major parts. During the Vivado phase, we will configure the block design, run design validation, and generate the bitstream. The most critical step here is to export hardware to generate an XSA file. This file encapsulates all hardware configurations and address mapping information, serving as the absolute foundation for our subsequent software development. Next, we will transition into the Vitis development environment, where we import this freshly generated XSA file to initialize our platform project and application project. The software development pipeline involves writing our C code, compiling the project, and finally running it via launch on hardware to load and execute the program directly inside the CPU. You can download the required source code examples for this course from the link provided. Next, let's examine our Vitis sample code. int main serves as the starting point of our program. First, we declare an integer variable named sw_out to temporarily store the switch values read back from the hardware side. Next up is xal_out32, this is the critical operation for controlling our hardware. This function issues an AXI write command, where the first parameter represents our mapped memory address, and the second parameter defines the specific data we want to write. Once this line executes, the GPIO register at that corresponding address updates immediately, thereby lighting up the specific LEDs on our board. Following that, we have sw_out equals xal_in32, this line performs the read operation. The CPU issues an AXI read request across the bus to the switch's base address. The GPIO peripheral then returns the current status of the slide switches, saving it directly into our sw_out variable. Finally, we print out the results to the terminal. Here, we format the output in hexadecimal to display the switch status we just captured, and then terminate the program. Through this single read and write cycle, we have successfully completed the basic communication workflow between a processor and a hardware IP core. Here is the constraints code for this lab. Let's start our project now. First, open up the Vivado tool and click on Create Project. Enter the project name lab4_example. Select RTL project just like before, and check the box for Do Not Specify Sources. Switch over to the Boards tab. Select the ZedBoard. And once initialized, you will enter the main workspace. Now, click on IP Integrator from the left-hand menu, click Create Block Design, and hit OK. Once completed, the IP diagram workspace window will open up. Let's click the plus sign at the top to instantiate our processor core. Type Zinc into the search bar and select the Zinc 7 processing system. After calling out the processor, click Run Block Automation at the top banner. This allows Vivado to automatically route the connections for fixed_IO and DDR, which represent the processor's dedicated input-output pins and memory interface respectively. Next, click this refresh icon at the top toolbar to clean up and regenerate the wiring layout. Once refreshed, you should see the layout clean up on your screen. Next up, let's instantiate our GPIO controller. Click the plus sign again, search for GPIO, and select AXI GPIO. Once it pops up, click Run Connection Automation just like before. Now, check the All Automation box and expand the GPIO settings down below. Crucially, change the interface option to LEDs. Because our physical output is going to be the onboard LEDs. Click OK. And then click the refresh icon one more time to clean up the layout. Once done, you will notice that Vivado has automatically wired the interface bus between the CPU and our AXI GPIO. It has also instantiated the processor system reset module that we mentioned earlier to perfectly synchronize all system clock and reset domains. Now, let's call out another GPIO instance. Click the Connection Automation banner at the top again, check the boxes, and expand the GPIO settings. But this time, make sure to select SW, which stands for the slide switches, as the target interface. Click OK. And run the Refresh Layout tool as usual to update your diagram view. Next, let's switch over to the Address Editor tab at the top panel. Right here, you can see that our two GPIO blocks have been automatically assigned to base addresses 0x4120_0000 and 0x4121_0000. Whenever the CPU wants to control these GPIOs down the road, it will interact directly through these specific memory mapped addresses. Once everything is verified, head back to the diagram view and click the checkmark icon on the top toolbar to run Validate Design. This ensures our entire block design is completely error-free. For the next step, go to the Sources window, right-click on Design_1 under the Design Sources hierarchy, and select Create HDL Wrapper. Choose the option Let Vivado Manage Wrapper and Auto-Update, and click OK. Once finished, you will see that the system automatically generates a top-level Verilog wrapper that instantiates all the underlying IPs inside our block design. Now, we need to set up our physical constraints file. Click Add Sources on the left menu, choose Add or Create Constraints. Click Create File, and name it Lab4. Once created, you will see the new file appear under the Constraints directory. Double-click to open it, and simply copy and paste our sample pin constraints code template right inside. Our next move is to trigger the compilation. Click Generate Bitstream under the Program and Debug menu on the left pane. Click Yes to let Vivado automatically execute logic synthesis and implementation. After the bitstream file is generated, click Open Hardware Manager to enter the interface. Now, we are ready to export our hardware platform to Vitis. Go to the top left corner, click File, navigate to Export, and select Export Hardware. Make sure you check the box to include bitstream. This is an absolute must because we need to generate the XSA file wrapper. Once exported, click on Tools from the top menu and select Launch Vitis IDE to open up Vitis. The tool will prompt you to initialize a workspace, which is where all your software projects will live. Click Launch to enter the Vitis dashboard. Once inside Vitis, click on Create Application Project. Switch over to the XSA tab at the top banner. And browse to select the XSA platform file we just exported from Vivado. Click Next. Now, enter our software project name, lab4_test, and click Next. Choose the classic Hello World template, and click Finish. After the workspace finishes initializing, you will notice your newly created application project along with the hardware platform XSA structure listed on the left Explorer pane. Expand the SRC folder, open up helloworld.c, and we will rewrite it to implement our required functions. Simply copy and paste our sample C code template right here. This code contains the foundational memory mapped read and write instructions for our experiment. Once you've entered the workspace, please follow the diagram to connect the ZedBoard using cables and turn on the physical power switch. At this moment, the green power LED will light up. Next, let's open our debugging terminal. Go to the top menu, click Window, navigate to Show View, scroll down to Locate Terminal, and click to open it. The terminal panel will appear at the bottom right of your workspace screen. Look over here. Click Open a new terminal, and select Serial Terminal. Please note that the COM port mapping varies from computer to computer, so make sure to select the correct port according to your PC's device manager settings. For the baud rate, choose our standard maximum speed of 115,200 and click OK. You should now see a connected status message at the bottom left, indicating our UART link is active. For the final deployment step, select our hardware platform directory under the left Explorer pane and click the hammer icon on the top toolbar to build the platform. The compilation logs will be displayed in the console window down below. Once that finishes, select our main application system directory and click the hammer icon again to compile our C programming logic code. The console will display the final build results once it's done. Finally, head over to the Assistant window on the bottom left, right-click on our System Project application, navigate to Run, and select Launch Hardware. Now, our compiled firmware is officially running inside the Zinc CPU core. In this specific demo snippet, the CPU writes a hexadecimal value of 0x11 to the LED register, which translates to 00010001 in binary. Because of this, you should immediately observe that the first and fifth LEDs, counting from the right side of your board, will light up. Furthermore, the real-time status of your slide switches will be transmitted back and displayed right inside the terminal window. For example, if you flip the fourth and eighth switches counting from the right side, the terminal will instantly echo the hexadecimal output, SW_out equals to 0x88. This perfectly matches the binary representation of 10001000. Now, feel free to toggle different switch combinations yourself, rerun the software execution cycle, and observe how the system dynamically responds to your changes. Here is the final demonstration of our Lab 4 results. Once successfully executed, you will see the outcome right here on the screen. Since we programmed the CPU to write a binary value of 00010001 to the LEDs, the first and fifth LEDs from the right side will light up. Later on, feel free to modify the code yourself, re-execute the program, and light up whichever combination you prefer. Additionally, as you can see, because the fourth and eighth slide switches from the right are currently flipped up, the terminal displays a hexadecimal reading of 0x88. You can toggle the switches arbitrarily afterward and rerun the program to observe the captured switch values. For instance, if you flip all 8 switches up, the terminal will output 0xFF. Looking ahead to our next lesson, we will dive deep into the bedrock of SoC communication, the AXI protocol. This protocol regulates exactly how data flows in and out of a system in an orderly fashion. In Lab 4, we acted merely as users navigating an existing address map. However, in Lab 5, we will take a giant leap forward. We are going to hand-plan our own construction site, assign customized house numbers to it, and finally move our custom ALU operation logic onto this plot of land, granting it a unique address on the map. Our core objective will be learning how to define the map, partition the address space, and design a custom hardware module that can talk directly to the CPU. I'm Albert. Thanks for watching, and I'll see you in the next class.